So according to our somewhat strange count, because we had 2 weeks of two classes and then weeks of one class, this should be lecture 9, I think. Although the numbers don't really make sense. And I wanted to start out by probably reviewing the last homework assignment a little bit, the tumor growth homework assignment. And then when we were done with that, going into the chemotaxis plugin and what we can do with that. Some of my favorite demonstrations of interesting behaviors are ones that involve chemotaxis. Some of these are things that you could do fairly easily in Physicell. For example, the self-generated gradient, I think, would work in Physicell. I think bacterium macrophage simulation might work in Physicell. The wound healing probably would work. Randy's never been able to get the angiogenesis to work in Physicell. So some of them, it would be interesting to compare the results. Some of them would be more difficult. And we could certainly think about why that is. And I don't know, were you able to meet with Pedro about the possible project ideas?
Oh yeah, we talked about it, and I'll go on design with a toy model design.
So
Say something. Yeah, but Pedro put up a very simple example and then try like simple things.
I think also for the cogeneration size part of things, I think Maciek is interested, and also Bart, who are neither one of whom is here, but are both available. They're both experts in CompuCell internal architecture and would be available to help out as well.
After this lecture, we could take maybe like 5 minutes.
That would be great to go over that. And Pedro's online, so if there are anything that come up that you want to discuss, we've got those. So my plan for the lecture today was to go over the tumor simulations a little bit. I basically had a couple of exercises written out, which were basically the homework exercises. And if you've already done them, you could show them to me and we could talk about things that worked or didn't work with those. And then we'll jump into chemotaxis. Chemotaxis is in some ways a very straightforward thing in CompuCell. There are a couple of subtleties, both in terms of the code. When you want to control chemotaxis on individual cells, then you have to use the Python to do it, and that Python interface is not always the most clear thing to use. I mean, typically when you're doing chemotaxis, at least in many situations, you don't want the strength of the chemotaxis to be the same for every cell. And then you have to use Python as usual to specify it. And that the syntax is a little bit non-obvious there. It's not terrible, but it's a little bit non-obvious. And there also are the usual questions about, there are some options about how chemotaxis works in CompuCell. So there are different kinds of saturated chemotaxis, that some of which are quite useful. The logarithmic chemotaxis is quite useful. The other saturation functions less so. And so it's not that complicated, but it is worth thinking about a little bit. Another thing that is particularly important in something like the bacterium macrophage simulation is the idea that in some situations, the chemotaxis depends on chemical fields that don't diffuse inside of the cells. They're only diffusing in the extracellular space. And so you get somewhat different results in that example because you only have the chemical chemoattractant in the field. And I think they were already in the slides from last week, but if you look at the slide deck, there's quite a bit of detail about both the biology of chemotaxis and the mathematics of chemotaxis, and also how CompuCell does it internally, that I didn't want to put into a lecture per se, but those are available as slides at the end of the deck. So if you wanted to go online and look at the extra slides, they're available to you. If you had any questions, we could go over that. So I guess I wanted to hear first a little bit, or we could do it afterwards, a little bit about what you're thinking about the project, and if there's anything you want to talk about. Now, if you want to save that till after class, that's fine too.
Okay.
Okay.
I'm working on this.
Pedro, can you hear?
Yes. Yes. Hello, do you hear me? Yes.
Yeah.
Right.
So, Pedro design. Oh, do you want to say something?
Yeah. So on the note of our meeting, James, we mainly discussed about the how to translate rules, and we started by implementing rules on CompuCell using for loops and other things. So we did two examples, and we took notes of all the possible challenges that we might face writing the translator, just to get a sense of how challenging it will be.
Great.
Yeah, so like in our model we include 3 basic behaviors, including chemotaxis, growth, and mitosis. So one thing that is quite challenging is that if the model exists already, like we wanted to add some rules. So that means like we have to add new stabbables into the Python code. So that leads to a question of like if the we made mistakes when inserting the like cell field on that line into the wrong class. So like to solve this question or the problem, I thought like maybe we should add this like entire stabbable instead of like making modifications inside of a stabbable. So that could probably lead to an error. So now the like I think very maybe should talk about that. So so now I'm like designing. So basically for the let's call it a rule project.
Right.
And there's a CC3D file and a simulation file.
Right.
In the simulation file, there are like a main pi and a stable pi,
Right.
stable pi. So I was going to insert a rule engine pi
Right.
into like the simulation file.
Right.
And also like another main pi for like inserting. So now I'm trying to like manually input some rules with it in the dictionary into the rule engine pi.
Right.
And then like the parser thing is like afterwards, but now like I'm just trying to manually inputting some like information into the rule engine pi, and the main pi could just and the rules, of course I have like I have a key to assign the behavior like classification, for example, like chemotaxis. So like the tab would be like object A, object B, and behavior.
Right.
and the hill function parameters like
Right.
the n, k.
Right.
But like a specific case is that if there are multiple factors like impacting the B. For example, if the B was the object that was impacted, and there are like maybe object A and C in affecting the B simultaneously, and they could have like synergistic,
Synergies.
yes, synergistic or competition.
Right.
So in that way, we probably have like isoforms or like more types of field functions.
So I don't know how Paul handles that. In other words, I remember asking him at the beginning, I said, what happens if you have more than one thing leading to one other thing? And at the time, he hadn't thought about it. So I don't know how he resolved that.
I think like by far it's still if A is affect B and C also affect B, and I have to like write it in separate rules.
Okay, right.
If you're using like the uniform way, like the
Right.
DSV to import these rules.
So one question is, when you do that, what order of evaluation do you have?
Order.
Or do you assume that the time step is so short that the order of evaluation doesn't matter?
Yeah, probably.
Because
think, like-
because if A modifies B and B modifies C,
Oh,
then the
okay.
order in which you evaluate matters, because the value of B will be different if A affected B first or if it is done afterwards.
So
And-
you mean like to consider them simultaneously or like in Paul's method, like to consider them separately or independently?
Well, so there are two things, one of which is what happens if you have some complex interaction where A, B, C, D, and E all affect F simultaneously. And it's not always possible to decompose that into the product of separate rules. But I think it's okay to start with something simple. The other one is more of a orchestration one, which is if you have finite time steps and you do the rules in different order and they depend on each other, then the outcome will depend on the order in which the rules occur. Because now if your time steps are very short, then in principle the order doesn't matter. But you have to then have a short time step to make sure that the change per time step of any value is small.
Well, I think like the case that you talked about should be considered more like a separate because it's depend on time. So for like a synapse, just for that scenario, like the two things existence are mandatory.
Right.
So in that case, like so like at this specific time step, you must like detect where the object B must detect the existence of A or
Right.
C signals. Could it have like process the behavior? So I think like that's just like a temporary thing, it's not like a time dependent, time series thing.
Well, it may be less of a problem. I think even if you only do some of the simpler examples, that's already very useful to have. So for example, implementing something like cell cycle that way could be quite interesting. Implementing other kinds of rules could be quite interesting. Again, I don't know the details of how that rule grammar, the concept of the rule grammar I know pretty well, but some of the more complex things that they've added onto it, probably I don't know. In other words, when I heard about it a few years ago, it was pretty simple. And even implementing that simple one would be already nice. Having a rule.py, of course, a CompuCell model can have as many steppable files as you choose. So rule.py can be a steppable. In fact, it needs to be a steppable because you have to inherit steppable base to have access to the dictionaries. So you're free to decide that just the way we have a default mitosis steppable, you can have a rule steppable. You don't need to put the word steppable in the name for it to be steppable. All it has to have is a load steppable base at the beginning. So I think using the dictionaries to control behaviors is probably a reasonable way to do things. And modularizing it the way you described is also appealing. So I think that those all seem like reasonable strategies to me.
Yeah, like the principle or the idea is pretty direct, but it's just pretty hard to test with them. So now I'm still working
Right.
on like manually testing and then like trying to parse, like if I just input the rules with text file instead of like now I already like input them into a dictionary, but like afterwards I have to use like the text information to put it into a parser, and then like the parser just transport these information to the rules
Right.
file. So yeah,
Right.
but we could like do it step by step.
Well, so the big question, I think, is going to be whether you actually use a parser or whether you essentially read and do code generation by hand. And Pedro, I don't know what your thinking is about this at the moment.
I think it's definitely possible to do, but there are many challenges because of how CompuCell handles variables, if I understood the question.
Well, so is your concern that you won't have access to the information you need inside a separate steppable? Is that the problem?
No. My concern is that it will be a lot of work because each variable is handled differently, and it depends on how the user defines the variables.
You
So
mean, for
the parser
example,
has to identify.
you mean if you're controlling chemotaxis, you have to do one thing. If you're
Yeah.
controlling cell volume, you have to do something else. And so it has to know for each process that you're going to control, it has to know how to interface with the particular parameters that can define that process.
Yeah, and you have variables in SBML, in MapBoss, you have user-defined variables in dictionaries, and all of those are handled very differently. And they could be handled, they could be declared in other ways by the user, and the parser has to identify how the user is declaring that. For example, using a dictionary, the parser has to detect where it's defined, how it's defined, to be able to include the rule.
So that seems to me to be a problem. A problem if you're trying to retrofit a rule set to an existing model. If you're building a model from scratch, then in principle, it could be up to the user to decide, okay, this lives in a variable, and now I have to have someplace which copies, in a dictionary, and now I have to have something that copies from the dictionary, say, to, in other words, there's a dictionary entry called cell.dict parenthesis target volume, and now I have to somewhere copy cell.dict target volume into cell.target volume. So my instinct would be to make all of the parameters and variables in the rule set be dictionary entries. And then if and when you get to that point, you add special rules that say this is how you copy from that dictionary entry to the chemotaxis parameter, to the target volume, to the lambda volume, and so on.
That's definitely possible. I think that might solve the issue. At least for a first attempt, having everything in cell dictionaries, and then later on, later on build like another tool, like separate from the parser, but that we can also definitely make part of the parser later that transforms some of these dictionary variables, or pass these dictionary variables into the appropriate variable like SBML, etc. But I think to start with, having everything in cell dictionaries, even like the target volume and lambda volume might be the way to go.
I mean, it could either be cell dictionary, or you could, if you wanted to, define a separate subdictionary, which was cell.rule.dict.
Mm-hmm.
But I mean, because it's an annoyance, but we already have this. If we want to do a tracking field for the pressure, we have to copy cell.pressure into cell.dict key pressure. If we want to copy things from the SBML dictionaries to do something else with them, we have to copy them from cell.sbml.key to cell.dict key. So we're already making, I think it would be nice if those things were unified, but at the moment, the user is used to having to copy things back and forth. It's an annoyance, but you have one loop that does the copy. And if initially the user has to write by hand a copy that does all those dictionary rules back to the CompuCell representations of those rules, it's still not that terrible to do it. It would be nice to automate it, but I think that's asking for a lot at this point. So my vision was that you'd compile the rule set into something that looked like a loop over cells and cell types, but I wasn't expecting to actually necessarily be able to write, in other words, to know this is the particular syntax for accessing chemotaxis. This is the particular syntax for accessing the chemical field. This is the particular syntax for accessing the cell adhesion. I was expecting that the user would have to do that glue code by hand to begin with.
That I think it's an easy problem.
Precisely to simplify this, yes. And I think if we did that, then there'd be more motivation also to go back and refactor CompuCell to clean up some of that. So that, for example, if you had automatically cell.volume and cell.dict keyed to volume, and CompuCell automatically copied those things back and forth, so that everything that exists as a cell dot object had a corresponding dictionary entry, that would simplify CompuCell use, because we spend a lot of time copying things back and forth in that way. And I don't think it would be that difficult for CompuCell to shadow cell.volume with cell.dict keyed to volume, for example. And that could be done in C++. It wouldn't have to be done in Python. Of course, it creates reserved keys in the dictionary, because then you couldn't use cell.dict quote volume for something other than the actual cell volume. So my instinct is to just use, ideally you would use the cell dictionary. If for some reason that doesn't work, you create a cell.rule.dictionary for it. But I wouldn't worry about that translation step. I think translating the rules by themselves is enough, plenty of work for a semester. And I think addressing the issue of the specificity and the non-orthogonality of the referencing of parameters and variables in CompuCell, that's something where if we had something like this, as I say, it might motivate us to go back and clean up and orthogonalize and regularize the code a little bit. So my suggestion would be to try to get a call in with Maciek about that, perhaps. But I'm pretty confident he'll suggest what I just said.
Yeah, I think we can have this done, like the dictionary entries, very soon. And then we can schedule a meeting with Maciek to see if we can standardize all variables. Because generating code, if everything is cell dictionary, I think is very easy. We can get it done in a few weeks.
Great. Well, I think that would be super valuable as an extension of CompuCell by itself, even if the user has to have another loop where by hand I copy from the dictionary back and forth to the particular named parameters and variables. I think that would be a big accomplishment. Now, I mean, it's up to you to decide whether you think that that's something you want to do for a few weeks, but it would be very helpful to us to do it.
If you like schedule a meeting, like join, like if you want to like talk about how to uniform and those variable names, can I join in your meeting?
Sure, of course. I don't know if you heard that, but she said that if and when you're going to meet with Bocek to discuss this issue, she wants to be included.
Oh,
So-
that's obvious. Yes, of course.
So I would suggest, have you talked to Maciek at all about any of this?
No.
Could I ask you, even if you don't set up a meeting right away, just tell Maciek that you're working on it with a student?
Oh yeah, I do that. Yes.
And no. I think TJ will be less enthusiastic about this, but I think maybe, I don't know. Maybe TJ will be more enthusiastic. But I think Maciek will be quite pleased to see this happen. And we've talked about regularizing things. I mean, the other thing I really would like, and I don't know if Paul, as I say, if the rules are exported as CSV, I would really like to see the rules exported as XML as well. Just to define a very simple set of tags that define it that way as well. Because again, if you wanted to incorporate the rules into an eventual cell type language, putting them inside of brackets to make them XML-like might be useful. And so if that's been done already, we should use that. If not, it's fine. We certainly need to translate it into Python. So it's mainly a question of, are you parsing the CSV file, or are you parsing the XML? And going back and forth between an XML and a CSV is a trivial thing as long as you know what your columns are named. So it's not a problem. As I say, I'm not sure you even really need a parser. In other words, for example, at the moment in Twit, there isn't really, it's not parsed. In other words, everything is interpreted by hand. There basically is Python that says, read, if you see this tag, do this thing, instead of having a formal parser for it. The only things that are parsed, I think, in the XML, really parsed are the mathematical expressions that use mu parser. Which is one reason that extending Wizard is such a pain, because you basically have to write every page of Wizard by hand. But all right, Well, I think that's, I understand your concern here, but I think even without doing that automatic final connection and leaving the glue for the user, I think it's still already very valuable. So if you want to have more discussion about that, do before you make a go, no-go decision. But I would be really glad to see this. I think it would be exciting to have it.
No, I'm happy to start this project already. It seems feasible, and we already have a pretty good idea on how to do it.
Great. Are you okay with that?
Yeah. I'm pretty excited to see
Great.
this happen.
Yeah, I think that would be neat. I think our friends at Duke would be pretty excited by it too. I don't know how Iran will feel about it, given how it sort of fit into his concepts about how to do things with vivarium. But one could certainly wrap this in a vivarium wrapper, for example. So I think it's exciting. Okay, was there anything more about project you want to talk about? No?
Not, yeah.
Okay, that's okay. We can there's no rule about that. We can always come back to it. So I wanted to come back to this tumor spheroid. And again, last week we got a little bit rushed at the end. We had started out that simulation when you're using thresholds, pure thresholds, for doing this proliferation quiescent necrosis. As you found out, what you get is really super sensitive to the threshold levels. And so that's why when I started teaching it, I'd say, okay, draw a tumor first, don't have any cell movement, and simply have the cells change type back and forth, depending on the levels of chemical that they're experiencing. There's a problem in CompuCell, and I don't think it's fixed, is it? Which is that in CompuCell, you're allowed, for example, one of the things that we talked about was having the necrotic cells not take up any oxygen, and the quiescent cells take up less oxygen than the proliferating cells. That was an exercise. And in principle, if you change the cell type, and those cell types have associated with them uptake parameters or diffusion or decay parameters, then automatically the diffusion and decay parameters should change when you change the cell type. However, for decay and diffusion constants, those are actually fields. In other words, there's a lattice which contains at each site the diffusion constant and the decay constant. And it winds up in the specific case where you use frozen cells. When you change the cell type, it doesn't automatically update the field values for the diffusion and decay constants. And so then you have to do that by hand. If the cells, did that ever get fixed in CompuCell, or is that still a bug in CompuCell, Pedro?
Which bug?
If you use frozen cells and you change the type of the cell to change the diffusion constant, for example, it
yes,
doesn't
I
update.
don't know.
It doesn't update the reason the place this came up was in doing those little cell membrane.
Calcium.
Yeah, the calcium, where you start out with the cells, you change one cell to be an ion channel, and it didn't work because the field didn't update properly.
Maybe with new TJ's diffusion solver, maybe it's fixed. I haven't tested the new diffusion solver.
Well, the issue was that CompuCell would update the values of diffusion and decay when the voxel value at a given location changed. But it didn't have something global that said once per Monte Carlo step, check if the cell type changed and then change the values for all voxels inside of that cell. And so if you ran the membrane simulation with the frozen cells and changed the type of one cell to make it diffusible, to make a ion channel, and that works, then it's been fixed. So maybe if you're listening in the background, you could run that simulation and see, because it's not a heavy thing to do to basically once per Monte Carlo step check have a list of all the cells that have changed type, and then iterate over the voxels of those cells and update the field at the diffusion and decay values. Just the way when you do a voxel change, it triggers these watchers. You could have a cell type change watcher that triggered. And that's a fairly minor thing to do, but it is core CompuCell development. So if you'd be willing to check that, I'd appreciate that. But I don't know. It's been on the list of fixes for years, and I don't know if it happened. Now, if your cells are not frozen, but have fluctuations, this is not a problem. It only affects frozen cells.
So like when a cell is frozen, like the core or the basic change was like, what was the basic change if you freeze it?
So we're talking about something a bit technical, but you can run into it. In the particular simulation we're doing here, where if the oxygen uptake changes when you change the cell type, and you specified the uptake rule not in the Python, but you specified the uptake rule in the XML. When you change the cell type in the Python, it may not update those parameters correctly. That's the issue.
Only for freeze. So
only for frozen cells.
So why is like a unfrozen cell would change automatically, but the frozen cell didn't change automatically?
So the answer was that to try to speed up simulation execution,
skip the frozen cells.
It skipped the frozen cells, yes. And it took us a long time to notice it because we don't use frozen cells that much. But when we do have frozen cells, we don't change their identity very much, because usually if it's frozen, the idea is it's always the same. It's only when you're doing something a little artificial like this one, where you change the type of the cell, but the cell is frozen, that you notice that when you do that, it doesn't automatically change all of the attributes of the cell.
So it sounds like you should just add like a checker, like
right,
for the
right.
updates.
Right. I mean, you certainly can put that in the Python by hand, but the code should do it automatically. You shouldn't have to do it by hand. So that's that was a bug that was reported a long time ago, and I was just saying I don't know if it was ever fixed. And I know exactly why and how it happened, but I haven't looked in the core code. The only time it really comes up is in that one thing where when you do the membrane, the frozen cells is a little membrane, where we had permeability. Remember, we had diffusion across the membrane. That one, you get it there, and then here in this example. When you're simulating real cells that move around, it doesn't come up, but it's in these slightly artificial cases, you notice it. All right. So we did the frozen tuber with type transitions, and the goal here was to look at the oxygen concentration in the frozen tumor first, and then try to come up with reasonable thresholds for the type changes. And then first to make the type changes work, and then to have the growth rate depend on the amount of oxygen taken up. And we include the concept of arresting metabolism. So the amount available for growth is the amount you take up minus some metabolic constant. Here it says that the growth rate can't be negative. In fact, if you have something like autophagy, of course, the growth rate could be negative. And then you have the cell grow at a rate that's some function of the amount taken up, which is more as the metabolism taken out. And the simplest thing would be to do something like a Michaelis function. The cell can't grow faster than some maximal rate, so you want a saturated function there. And so I guess then we come back to the homework, that was the homework assignment. And I wondered, you said you wanted to talk about how it went for you. These exercises, if you go to the Google Drive in the student materials folder, these exercises are all there. Because the course lecture, the lecture identities may not be the same as in previous years. You may have to look around to see what folder they're in, because they're demos for lecture 1, lecture 2, lecture 3, lecture 4. Those may be out of date, but the exercise, in other words, exercise 10_2_ avascular tumor, part 1 or part 2, those I've checked that those exist and that they run, but they may not be in the right place. But how did you do with this when this was, as I say, as a homework exercise? You said you wanted to talk about some of these. Was this one of the ones you wanted to talk about, or?
It's not that one. I think it's the microbial, like.
Oh, the microbial one.
Like cross.
Oh, okay, fine. Okay, so this one, you got this one to work, where the cells at the surface of the tumor are proliferating and they grow. And so you'll see gradually the number of proliferating cells will go up. The number of necrotic cells will gradually go up as you get a necrotic core. So you get something that looks like that. That's pretty sensitive to the thresholds for conversion. And so that's a pretty tricky one. That was doing the thing without cell division. And then when you include cell division, you get, and of course, then the cells stay roughly the same size. The shape of the tumor doesn't change very much, but you get some irregularities. Why do you get white, blue again? That's because we defined a hysteresis where the threshold for the cell going from proliferating to quiescent was at a lower level than the threshold to go back. If you set the threshold for quiescent to proliferating and proliferating to quiescent to be the same value, then your cells jump back and forth all the time. And so that simulation isn't really realistic. Once the cell's gone into quiescence phase, it needs a higher level to kick it out. And so you need to have a bit of hysteresis, which is why you have this irregularity in the shape of the boundary between quiescent and proliferating. Since the conversion of quiescent to necrotic is irreversible, you get essentially a well-defined boundary here. you do get a little bit of roughness at the surface because, for one thing, there's no cell sorting. We don't have a defined contact energy so that the necrotic cells stay compact. We also haven't turned off the fluctuations in the necrotic cells. In principle, the necrotic cells shouldn't have active fluctuations. It's possible to do that, although we haven't talked about how to do that. And you could argue also the necrotic cells should shrink and disappear as well, although
That probably happened as well.
right. Although it depends on the cancer type, how fast they disappear and whether they leave behind some kind of material, non-diffusible material. And of course, if there are no macrophages or in the region, they may not get cleaned up. So there are a bunch of biological questions about that. So that simulation was based on starting with a cluster, and then I said, well, let's start with a single cell and see what happens. And you basically get the same thing. In this one, I must have triggered this one on target volume because you see these synchronous oscillations in the green where the cells divide, so the number of cells goes up. So you have a lot of cells dividing at once, and then those cells convert, some of those cells convert to being quiescent. So you see the number of quiescent cells jump up. And then once you start getting the necrotic core, you get the same thing where you get, well, immediately after cell division, you have more proliferating cells, and then you get conversion of them to quiescent and then to necrotic. It looks to me, and I would have to look back at this code for this. I think the rule that I wanted was that immediately after division, the cells become quiescent, which is generally true for cell division. And I don't think that's implemented here. I think the proliferating cells stay proliferating after division in this simulation. And then the other thing that this is quite sensitive to is the diffusion length. If the uptake rate and the diffusion constant are large, then of course if the uptake rate is low and the diffusion constant is high, then the oxygen gets further into the tissue. And so for given thresholds, the thickness of the proliferating and quiescent layers is thicker. And so you can see that. And so, and then the last step was to say, well, what if the necrotic cells disappear? I suggested reduce the target volume by 1 voxel per Monte Carlo step. That's actually pretty fast. It's actually much too fast, really. You're going to get, and you get mechanical instabilities. And so then you get these kind of branched morphologies because there's a continual flow of cells into the center of the tissue rather than and that leads to mechanical instabilities. You noticed already, I think, in your bacterial simulations that there's a problem with doing diffusion on a square grid when you get close to the corners. Whether you use fixed boundary conditions, periodic boundary conditions, the corners are different from the other parts of the boundary. And so you tend to get accumulation of material or disappearance of material preferentially in the corners.
Like all of cases you can just observe like the boundary, especially at the corners, like has higher value than other places.
Yeah, well, if you have a source of chemical from the outside that's diffusing in, then you definitely get more at the corners. Because if you think about it, suppose you have a constant flux boundary condition on the boundary, which is supplying chemical to the system. And now you ask, now how much chemical is available at a given point? Well, the amount of chemical that's available at a given point is basically the integral of, well, e to the minus distance divided by the diffusion length integrated over the boundary. And if you do that integral, if you're in the middle of an edge, effectively you're near just one boundary. You're near the nearest boundary. If you're near the corner, you're near two boundaries. And so the supply is about twice as much.
Yeah.
Now, it's not exactly twice as much because things aren't linear because of that exponential decay, but nevertheless, you expect that the concentration will be almost twice as much right near the corner as it is in the middle. And so you do get extra chemical that way. Now, that's for constant flux boundary conditions. If you have absorbing boundary conditions, then the flux is going the other way. Then you have lower concentrations at the corners than you would in the middle. And if you use constant value boundary conditions, then it's a little bit better behaved. So instead of having constant flux at the boundary, if you fix the value at the boundary, it's better behaved. But even then, if the cells get near the boundary, you have still the point that if the cell is near the boundary in the middle, it's interacting with one boundary. If the cell is near the boundary in the corner, it's interacting with two. And so those corners do have fundamentally different properties. And so your best bet is to try to keep the cells away from the boundary, stop the simulation while there's still some boundary, so you're not too close. If you can use periodic boundary conditions, then you often do a little bit better. Even then, you can get some corner effects. But periodic boundary conditions, in principle, the boundary is well behaved. Now, with diffusion, if you really want to represent an infinite source of chemical outside of the field of view, then periodic boundary conditions don't work for you, and so then you have to decide what you're going to do.
In my exercise, well, the last question just requires you to enlarge the lattice size.
Yeah.
So you can see like it's quite actually that one is quite different from previously observed cases. Yeah, like just simply enlarging the lattice size, you can see like actually the good when
Did you want to screen share it or?
Oh, yeah, probably I could show you like there's a screenshot of like or actually it might be like if I set the lattice size as like 200 by 200 and the cells just of course the cells will fill up the like the domain because the lattice is very small. these pictures, you can see like this one is with 300 by 300
Yeah,
by the sun.
yeah.
You can see like it just forms a round aggregate.
Right. So there you have periodic boundary conditions for the cells.
Yeah, it's like
Is the chemical field also periodic?
chemical field. Probably like you can see.
Which is the
So this was A nutrient, this B.
Yeah.
And this is the starves status.
right?
I count like how many times I like how many Maxcala steps the cell is being at the kind of starvation
Right,
status.
right.
And if like the starvation lasts too long, they'll die. So this is like a counter to show you like
Neat.
like these comes
Right.
these cells are going to die if they keep starving.
Now this is the simulation of bacterial growth, right?
Yeah, but like because you mentioned
Which is not very different from I mean,
Yeah.
it's just it's a fairly straightforward extension of this simpler simulation.
yeah, like you can see this one. Yeah, like this one is definitely I think is kind of disturbed by the boundary because you can see like the boundary conditions are very different from the
Yeah, that's the classic thing that happens when you have fixed flux, constant flux boundary conditions
Yeah.
on a square.
So like until I finished the last
Right.
simulation, I realized that maybe like the previous simulations were not that correct.
So
yeah, it's just pretty much
Yeah.
a lot of sense.
yeah, so they're and I don't have a really good workaround for that one because I mean, it's computationally expensive because you have a lot of empty space in your lattice. But one workaround is to use quite a large lattice and then draw a circle of frozen cells and have that behave as a source. So that the source is coming from a circle, not from a square. Then you don't have the corners anymore. But of course, then the simulation has these big regions where nothing is happening outside of the circle. And so it'll run slower. But that works. The periodic boundary conditions work pretty well too. But then you have to decide where the nutrient is coming from. Now in a simulation like the one you're doing, if the primary, in other words, if there's a little bit of background nutrient, you could have the background nutrient be available everywhere, but and then have periodic boundary conditions and have the nutrients or anti-nutrients secreted by the cells themselves move around the boundaries the way you did it here. And so that works. The other way to do it, which we'll do in these cancer simulations sometimes, is so in the cancer simulation, as you point out, eventually, because the nutrient is supplied by the boundary, the cells always grow to fill the whole space. But if you have the nutrients supplied by the medium, so the medium secretes nutrient, then as the tumor grows, the amount of nutrient available goes down. And so then you'll reach an equilibrium where the available nutrient balances the consumption by the tumor and the growth will stop. Now you can get oscillations if you're not careful with that, where the tumor will overgrow and then shrink and then overgrow and shrink. But when you have the nutrients supplied by constant flux, then the amount of nutrient available per unit time is constant, doesn't depend on the configuration. If the amount of nutrient, if the nutrient is supplied by the boundaries with constant value, the supply of nutrient goes up as the cells get closer to the boundary, because the gradients at the boundary become steeper, and therefore you actually are pulling more nutrient in per time. And again, if you have constant value or constant value or constant flux doesn't really matter. If you have that supplied by the medium, then as you have more cells, you get less nutrient supplied. So you essentially have three possibilities. Constant flux, there's a constant amount of nutrient available per time, whether you use it or not. Constant value, the more you use, the more you supply up to some maximum. And medium supply, the more cells you have, the less nutrient is made available, and therefore you get self-limitation. And so those are the kinds of situations where it would be very tempting for me to write lots and lots of homework problems to do all of those, but it would be too much work for somebody to explore all of those. That's a case where having a demo may be where you could, everything is predefined and you could just switch. You have, select one for this case, select two for this case, so you could run it without having to write the code to generate it. Could be interesting. In the days when we put everything up on NanoHub, we had some cancer demos that were like that, where you could configure the demonstration to do a bunch of different cases of that kind. Didn't have that particular set. Somewhat similar. So what did you want? But I mean, the one thing is, if you're not on the Zoom, you can't screen share, and so Pedro can't see your results. Or we could share your homework and we could all look at that together. That's from your homework problem, right?
Yep.
Let me see if I can pull that up. Maybe I can pull it up and we can look at it together that way. So,
For this one, I think because this assignment is assigned by Pedro, and he applied like some codes for a basic model, and I think all the nutrients are secreted from the medium. So I think like for the previous cases where the cells fill up the domain is because the lattice size is too small. So it's just like it will reach there.
so let's see. All right, can I drag this to? It's a screen share issue. I'm trying to see.
Maybe you could just open the file and so it's
Right, well, that's what I was trying to do, but it's not. I don't know why. Let me try again. No, I had the PDF file open. I've got it open, okay. But I don't know where it went. I can't see it.
It's not on the.
There's Acrobat shows that it's open, but it's not visible. I don't know what happened to it. That's a different one. What is it? I don't know what happened. I don't know where the
You to where the slides.
let's see. I don't know. Something strange happened to the way Acrobat is displaying. It's put the it's put the display off of the out of the field of view. Let's close. Sure.
Oh, so
So this is open. It's open. And here's Acrobat controls. And if I go here, it says that your text is open. But it's not displaying it. And I don't know why it's somehow the
just not use Acrobat. Use like I think like this browser can also
open with Chrome. Okay. Okay. Yeah, if I open with Chrome, it's on. What happened was somehow when I tried to move the display from this window to the shared display that's on the wall. When I did that, it put the image somewhere not in the field of view of either computer screen. So it's there, but it's on it's off outside of the field of view of so I don't know how that happened, but anyway, okay, so here we are. Okay, so now we got it. All right. Sorry about that, but and I don't know why Zoom would do that to me, but it did. So okay. So here we are. So here's your homework. And I'd like to make the image a little bit bigger maybe, but here we are. Okay. Is there a full screen option? No, I'm not going to fuss with it. So which page do you want me to go to?
Oh, like maybe like this page and the last page.
Okay. So here, Pedro, this is really for you. Can you see this? Are you seeing this, Pedro?
It's loading. Yeah,
Okay.
I see it.
Because this was really a problem you assigned. So the questions really
Hmm.
we have to have you involved in it. And so so what was your concern about these results? So the first thing we were talking about was you're getting these high concentrations at the corners because the boundaries, you've got two sets of boundaries for the corners.
Yeah, I think like so the first concern about this tumor situation, the lattice size is quite small. Given the condition that all the nutrients are secreted from the medium, that means like we are supposed to reach like equilibrium, but
Right.
in the previous cases we didn't see that because just because the lattice like constraint or limitation. So
Well, so you want me to go back to the tumor simulation?
oh no,
This is all the
this is all
this is all the bacterium.
oh wait, this is all for the microbiome. Oh, it should be fine. I think like it's just the same case because
The same issue.
the same, yeah, because like you didn't change.
So the background nutrient is supplied by the medium only, is that right?
Oh,
Do you want me to open the code? Let's see if I can find the code.
no, somehow.
Okay, so you want me to look at the microbiome simulation?
Yup, and the XML, or if it's pretty hard.
Okay, so which one? Ecosystem 2, or inhibition?
I think for this one, ecosystem is okay. So.
Okay. And so you want me to look at simulation?
I think it's defined in XML, like you see the nutrients created by the medium.
So I have to reshare here. So in this case,
So and the XML. Or there's the HTML.
yeah, so let me open it in Twitter.
It's fine, it's just confirmation. But the real problem is not this one, this.
Okay. So here is the code. All right. So let's look at the XML.
The definition.
After okay. Now I'll look at the diffusion equation.
Maybe something new.
So the diffusion coefficient is defined in the cells. There's a global decay constant. And medium secretes at 0.1. And the decay constant, the global decay constant is 0.01. So the equilibrium concentration is 10. Equilibrium concentration of the chemical is 10. And so we can calculate what the maximum secretion rate is, which would be basically 0.01 times the number of voxels in the system. So that's the maximum available nutrient. Okay. And this is the waste product that's done in Python. And you have the other waste product, and that's also done in Python. Okay. And the concentrate, and they're both periodic boundary conditions. Okay.
So the real problem is that I mentioned it in my assignment.
Yeah.
So as you're simulating the cross-fitting case,
Right.
like so at the beginning, the cells fill up the domain and the 4 localized starving regions, like because it filled the domain and the oxygen, not nutrient or something, didn't diffuse to the central part. So some cells begin to starve.
Okay,
And
that sounds like what I would have thought that's what you want, but maybe.
yeah, that's what I want. But after like they're starving for too long, they begin to die. So like in the middle part,
Right.
some cells begin to like crash and
So-
then like all of the cells are, oh yeah, like because like the domain is filled and the starvation part is also expanding, and all of the cells are just like experienced and kind of an update, and then they just didn't do anything anymore. I was kind of like curious about this because you can see from the window of which records the starvation status, all of the cells like are starving and keeps starving because you can see the number increasing, but they just don't crash.
I don't know I'm not sure I understand what you mean by crash.
And like if they starve for too long, and I just turn the lambda value to like 10,000,
Yeah,
and the target value to 0,
right. So then they should shrink and disappear.
yeah.
But that will only work if there are some medium left. If there's no medium at all, then they can't. So this is something that was debated a long time ago in CompuCell, which is should medium be should you be able to nucleate medium or not? Because if you get rid of medium completely, then when the cells try to disappear, they stretch other cells. There's no way to regenerate medium.
Oh. Yeah.
And so that can be
Yeah.
a problem.
So, James, in the homework, I put a link to a simulation that I did on this problem. And
Yeah.
when the cells die, I draw medium in the place of the cell, so I don't shrink them to death. And that
Okay.
allows you to get all the patterns without artifacts from the lack of medium.
Do you want to screen share and show your simulation?
Yes.
I'm on my cell phone, but it's on the link in the homework. She has access to it.
So this is, sorry, this code is the code you wrote, or is this the code that Pedro wrote? Okay. So this is supposed to be your code, Pedro.
Yeah.
Hmm.
You see, like there's a banner of your name and the.
Okay, so then I'll have to take a look.
You're like.
Oh wait, are you running? Is this one the one I sent?
Yeah. Yeah, and the letter size is quite large. It's 3. I'm not
Yeah.
sure.
Now I'm surprised it's so slow, but anyway. Is this updating? I think what happened was, no, I think the screen's frozen is what happened.
It's pretty slow. Like yesterday.
No, yeah, but no, when I was fiddling with the settings, the display, the player will sometimes, and I don't know what causes this, player will sometimes fail to update the screen. So even though you see it going through Monte Carlo steps here, if I look at a field, this isn't updating.
I think it is.
This one maybe is. It's okay. Some of them I thought were not. And then in that case, if you click on the field, it will update it. And I don't know why sometimes the field the image they freeze. But this isn't the world's fastest computer. That doesn't help.
Not sure if this would.
I mean, it could be that I sent the wrong file, so I'll have to check.
You like send you the code?
I mean, we can look at the code. So, the things in the XML all look pretty well behaved. You have a nutrient that's secreted by medium at a constant rate. And then you have waste and A and B that are not produced. They're going to be defined in the Python.
Mhm.
Let's look at the Python. Oops. So what do we have? You define the cell volumes. You have a starvation counter. You have a scalar field for the starvation status. You pull the field secretors at the beginning, so you don't have to keep repeating that. That's a good way to do it. Now, what are you doing? Nutrient. So you've got some counters. You pull a reference to starvation field.
To calculate the growth.
So you go through the cells. It's cells of type B. You take up waste A. Okay. You take up the nutrient. And you secrete the waste B. That makes sense. Okay.
One place for the density skip that. And then I calculate growth amount based on nutrients. And waste A with this microtype.
Right. So growth amount is. Okay, so what's happening here?
Because they're both negative values, so you just like choose the
Smaller one.
Yeah, like absolute value smaller one.
Right.
And I set the growth amount is based on the smaller value.
So they're both limiting. Whichever you have less of determines the growth rate.
Okay. Yeah.
Okay.
And if the growth amount is like a bigger enough, so you just like recalculate the starve power,
Right.
because you don't want a large.
If they're actually growing, they're not starving. So okay, fine.
And if the growth amount is small, here I can call it.
Okay, so this is determining whether or not they're starving. Okay. And now, and that's true for all cells. And now where do you actually do grow? Oh, it's only for cell type B.
Yeah, so for cell A did the same thing.
Except reverse.
Yeah.
Reversing the field types. Yeah. Okay. And so here's the target volume is to growth amount. Okay. So, I mean, this seems pretty reasonable. The only thing maybe is that there's no resting metabolism. So the cells don't need, in the cancer simulation, we said that you take up nutrient, but only nutrient minus some amount is available to grow because the cells need some amount of nutrient per step. But to begin with, this is fine. I don't see any reason. You don't need a resting metabolism to start out with. Okay. And now, if the cells get to be too much starved, you kill them. Okay. And then if the cells get to be big enough, they divide. And they inherit the target volume. And E is the energy the cell has, the stored energy.
Yeah, it's something the paper set like right as rules because like it's kind of like equal to the starvation status.
Right.
So
but-
the averages
right.
below 0, you just kill them.
Okay. But here you don't have it turned on. Well, it'll inherit the original value, not a changed value. Okay. All right. So, I mean, this all seems pretty reasonable. I mean, none of it, I don't see anything here that looks strange.
Yeah. So I'll probably run this on my own computer because it takes time. So maybe like when I was running it, you could just go ahead and your like the remaining lectures. And
Yeah, it seems to be running pretty slow, but these also are not updating. I think, yeah, I see they're not updating. So what happened, as I say, sometimes when you mess around with the player, especially when you move it between windows on your computer, the way I did, I had it on this screen and I moved it up there. Sometimes, boy, why is it showing news? Just what I want is Windows to be popping news items up on my shared screen. But yeah, this looks in, so
well, I think like I'm not
so what I don't see here was where the cell field is here. Why are all the cells?
kind of like a radio because the like you see like the innermost cells are dying, so they should
Right. Okay.
So
For
it's
some
just-
reason, I was having trouble seeing the cell color. Okay. So this looks pretty reasonable since you get clusters of red cells and clusters of blue cells, and they're radial.
yeah.
And you get these lines, these radial pie slices of cell type. And that's observed in experiment when you do this.
Really, I
Yeah.
have no idea. But
There are simulations and there's simulations by Nelson of all people from Harvard, where he did simulations of this kind. And you do get these radial stripes where one bacterial species will go out to the surface like this and another one will go like that. And they're not perfectly uniform. Sometimes they disappear, sometimes they split. So this now if you didn't have the dead cells disappear, but just turned them off, so they didn't metabolize, but they didn't disappear, you might get a bit of a different result.
yeah, I think like the innermost cell diet is part of the reason that stretched the
Right.
to form this kind of like
Right. So
radio.
yeah, so one problem with CompuCell on a lattice-based method is that there's a drag, which you don't have in PhysiCell because you're off lattice, is that there's a drag on the cells against the lattice. And so if I have a cell and I push on it or pull on it, it doesn't move. First, there's a minimum force I need to get the cell to move at all. And secondly, if I pull too hard, the cell will break. The cell will not be able to move artificially fast. And so there's no rigid body motion. In other words, if I have a line of cells like this, and I pull on one end of it, the line will stretch. The front cell will move more than the next cell, will move more than the next cell, will move more than the next cell. Eventually they'll all move, but this line will stretch. And that wouldn't happen in reality. In reality, the thing would move as a single rigid object.
Because they're rigid.
Right.
Is that like a tangle?
And it's because they're sticking to the, it's as if you were on a substrate like this that was sticky and you're pulling on the front. And so the lattice behaves like a sticky substrate.
Oh,
And so if you if the two ways of dealing with that, of course, the simulation is already pretty slow. If you make the disappearance of the cells slow, really slow, then the thing will be more equilibrated. And so you'll have less of an issue with that. And if you actually couple the cells with links, so you actually create a rigid linkage between the cells, then it works better too. Although that's more work, and you haven't talked about how to do that.
okay.
So, but here it looks okay. If I'm looking at this, I see medium is, the cells are dying and being replaced by medium, which I think is what you want, isn't it?
Mm.
So when you look at this simulation, what is it about this simulation that you're worried about? What do you think is wrong with the simulation?
With this one, it's okay because this one's used with a 300 by 300
Right.
lattice, but here I tried with 200 by 200 lattice.
Yeah.
It's not there yet, but so it might take 1 minute
Yeah.
to get it there. So if you want, so I'll continue your like
Okay.
All
right.
And I could just
But I mean, I haven't done this exercise. Usually I don't assign exercises until I've done them myself.
it's okay.
But since Pedro wrote this exercise, and I'm not blaming Pedro if something's not right. I'm just saying, since Pedro wrote this exercise and it's new, I don't know. I'm afraid I don't know all of the details about what might or might not work with it.
Instructions, it's very good exercise. So.
But definitely you could add, this is something that if you were going to give the exercise again, you could say, what is it? How could you, what should you look at, or what is confusing, or what parameters to change, or what should you analyze? Because we haven't, until you've played with these things, it's hard to know. But to me, the fact that you're getting basically a circular growing region with these stripes, that is actually very typical of how biofilms grow. When you have two species biofilm growing from an initial core, you get exactly that kind of pattern. So, which is not I'm not trying to say that it's right per se, but that kind of morphology that you're seeing here doesn't seem to me to be, there's nothing obviously wrong about it, which is different from saying that it's right, but it's not obviously wrong to me. And I'm happy to come back and talk about that. All right. So while we're doing that, the next topic that we have is cell movement, taxis. And typically we model what we would call chemotaxis or chemokinesis. But in fact, we know cells can respond in movement to all sorts of things. They can respond to the rigidity of the substrate, which is durotaxis. That's actually fairly hard to implement computationally, although people like Roland Merks have done simulations of that. They can respond to electrical fields. It's not that hard to pretend that the chemical field is an electrical field, so that one's not so bad. External gravitational field is really easy to do. Temperature field, again, since temperature diffuses, so temperature field behaves like a chemical field. The substrate rigidity really doesn't behave like a chemical field, which is why it's a little bit harder. light level phototaxis. There was some beautiful simulations done, almost 30 years ago by Stan Murray, where he actually did simulations where he calculated, essentially, he did ray tracing to calculate light exposure for cells in a simulation, not using CompuCell, using a different package. And it had very interesting things. He could actually get phototactic behavior purely from modulation of, in the phototaxis, there was a particular chemical reaction in the cell that was modulated by the light availability, and that was enough to get the cells to crawl up gradients of light. That's a beautiful paper. Of course, acidity can be a source of external fluid flow. We can't really do because we don't have a flow implemented. Variable stress and strain in the environment also is one that's hard to do because we don't have the mechanics of solid materials. Again, Merckx and Renz did simulations about that. And then the one we do the most often, which is chemical concentration. And when we're thinking about this, the questions that we ask are very much like the ones that you have in your rule set. Where is the signaling molecule? Does it diffuse freely in extracellular space? Is it bound to the extracellular matrix? A lot of chemicals actually don't diffuse freely. They bind to collagen, for example. They'll have a heparin binding domain. They'll bind to collagen. And so actually you're following gradients not of a diffusible chemical, but of a chemical that's bound to the extracellular matrix. Often it behaves very similarly to a diffusible chemical, but it's not quite the same. And then does the chemical actually go through the cell everywhere, or is it taken up? We often assume that the diffusion constant is the same everywhere, whether there's a cell or not. In reality, oxygen that would be true for, but most molecules don't cross the cell membrane very well. And then if you're doing a 2D simulation, if the chemical is actually in the substrate, then the chemical should diffuse everywhere. Cells don't do anything to it. If the simulation really, if the cells really are thought of as 3D and excluding the chemical, then you have to know that. And then you also have to ask the question, typically we don't do advection. When the cell moves, it doesn't change the gradient directly by its movement. It doesn't carry chemical with it. We typically want to neglect that. If the cells don't move very fast, that's okay. If the cells move quickly, then it's a problem. And then also, when you receive a signal, typically, if the cell's actually taking up chemical, you're reducing the chemical in the environment by a lot. If the chemical is binding to a membrane receptor, usually you're not using a lot of it, but sometimes the receptor, once it's bound, internalizes and destroys the signal. Sometimes the signal is released. But the key question is, if you're taking chemical out during signaling, how much? Is it enough that you actually have to worry about the uptake? And then all the questions about the receiver, when a cell's receiving a signal, do they have the signal receptors everywhere, or only on one surface of the cell, or only in regions in contact with some particular target? So, for example, there are receptors that only respond to membrane, to extracellular matrix bound signals, not to the same molecule if it's in free solution. And sometimes it's the opposite. That cell will respond to the signaling molecule in free solution, but not when it's bound to the extracellular matrix. And then because the cell is an extended object, does the cell sense the direction of maximum or minimum concentration, direction of steepest ascent, or something else? Typically in CompuCell, there's an option. You can have the chemotaxis apply to the center of the cell, which the cell responds as a unit to the gradient around it. Or the chemotaxis can act on each unit of the boundary independently. And those have very different, in some cases they behave very similarly, but in some cases, if the concentration is changing rapidly in the environment, the behavior of the cell is very different if the chemical gradient acts at the center of the cell versus at the boundary of the cell. And this is why I'm saying that in principle, chemotaxis seems pretty simple, but there are a lot of choices that have to be made. And those choices really are reflecting the biology. All of these things happen in different biological contexts. And then we typically don't model adaptation, but we know that in many cases, if the concentration of the chemical is high in the environment, the number of receptors is reduced. And so because one of the problems we face with chemotaxis, simple linear chemotaxis, is that if the chemical concentration varies by a lot, there are some regions with low concentration, some regions with a high concentration, then the response of the cell isn't really what you want. The cell ignores gradients for low concentration and moves too fast to high concentrations. In reality, cells are more likely to say, if there's enough of a gradient, then I move in the direction of the source at a velocity that's more or less independent of the concentration. And so you have what's called perfect adaptation in those situations. And that's not something that's so easy to simulate. You can do it by hand, but especially when you have spatial variability over the membrane. And we know that there are situations, for example, if the chemical concentration is too high, the receptors are saturated and the cell stops responding. So you have a situation where for very low concentrations, there's no response. At intermediate concentrations, you have response, and then at high concentrations, you don't respond again. And then, of course, how does the cell respond to those bound receptors? We're not modeling the receptors and their binding. In principle, we should actually model the kinetics of the binding and unbinding of every receptor and possibly internalization of each receptor, but that would be a very expensive simulation to do. So we tend to ignore that. And then also there are situations in which, and the dictyostelium is a classic example of that, where the cell monitors the signal in the environment and then moves in response to that signal and then stops and then ignores the signal. There's a refractory period during which the cell doesn't respond. So the same signal has a different effect on the cell depending on the internal state of the cell. So there are a lot of possibilities here. We only implement a fairly limited range of these possibilities. And then once you have the signal, you have to understand what the cell does. In particular, does the cell move when there's no signal or not? Does it move randomly? Does it move in a directed way? Is there some threshold below which the cell doesn't do anything? As I mentioned, the cell may respond as a whole. Your bacteria are going to respond as a whole because they have rigid cell walls. But if you have something like a neuron, which has projections, the individual projections will respond to chemical signals in their environment independently of each other. So basically, little patches of the cell membrane go and behave as if they were independent cells. And their subcells are sort of intermediate to that. Endothelial cells, vascular endothelial cells, different patches of cell membrane can respond a bit differently. And in reality, there are molecules like PIP2, PIP3 on the cell membrane that define where protrusion happens and where retraction happens on the cell membrane.
Yes.
What is it? Phosphatoinositol diphosphate and triphosphate, I believe. PIP2 and PIP3.
Oh, so some like specific molecules.
So these are molecules that are membrane bound molecules,
Oh,
and they tend to PIP2 and PIP3 repel each other in the membrane. So they coalesce, they sort to make rafts. So you get regions of high PIP2 and regions of high PIP3. And one of them promotes protrusion of the actin cytoskeleton, and the other one promotes retraction of the actin cytoskeleton. And so when you have polarized cell crawling, that is mediated by localization of PIP2 and PIP3 to regions of the cell membrane. And I mean, we don't usually simulate that, but oh, I don't know, almost 20 years ago, Giulio Belmonte, who was a student of mine, did some beautiful simulations of that. And I think they may finally be published after 15 or 20 years. For various reasons, he did that work maybe not 20 years ago, 15 years ago. I remember we started working on that when we were in a meeting in Barcelona. And anyway, for various reasons, it never got written up. I think he's written it. I think he just published something on it finally. He's talked about how to do it. He's actually talked about how to do that simulation. Their lectures. If we get to it, I could go through those lectures. There are lectures that he gives in the summer course that explain how to do that. And then what's the relationship between signal amplitude and cell velocity? As I say, in a lot of cases, the cell basically either moves or it doesn't. Once it starts crawling, it crawls with a more or less uniform speed. And then is the movement quasi-deterministic, or is it via biased random motion? Typically, bacteria, you have chemokinesis where the bacterium tumbles and then moves in a straight line for a while, and then it tumbles and randomly orients and moves in another straight line. On average, that will move up chemical gradients, but it's very different from directed movement of a eukaryotic cell. Although I know they've also found bacteria that can actually follow gradients directly. The bigger bacteria can do that. And then if you have conflicting signals, of course, you have to ask the question, how do those conflicting signals integrate? The naive thing would be that they're like in Paul's rule grammar, that they basically add, but in fact, they might not add in a simple way. There might be nonlinear combinations. And then also, typically, we're going to simulate the cell movement as continuous, that if there is a chemical gradient, the cell moves with a constant velocity or roughly constant speed. But in fact, in a lot of cells, bacteria, both bacteria and eukaryotic cells, the motion is pulsatile. The cell will move for a while, then stop, then move again and stop, and then move again and stop. Of course, if you have something like chemokinesis, where the bacteria runs and then tumbles and then runs again, that's clearly a pulsatile movement. But eukaryotic cells also do that. So there's all this complexity in the biology, and as usual, 99.9% of models ignore all of that and do something very simple. So I don't know if these videos are going to work. We'll see. Perhaps the classic example of chemotaxis in eukaryotes is dictyostelium. And I hope the audio doesn't play because these have horrible background audio. We'll see. So this is a experiment. I should have the. And so here you see they have a micropipette. And this micropipette is releasing cyclic AMP into the environment. And these cells are crawling towards the source of cyclic AMP. And so this seems like a pretty simple case of chemotaxis to a gradient. In fact, if we had a little bit longer movie, you'd find that, and maybe these cells are not behaving normally. Those cells would behave in a pulsatile way. They'd move and then stop, and then move and then stop. Famously, and these are the simulations that Stan Murray was so famous for. He did already 20 years ago simulation of this whole process. You get these. Oops. You get these, sorry about the sound. You get these macroscopic, these are aggregates where cells, the individual cells cluster, these are the same cells. So here the cells by themselves are moving randomly. Then they start sending signals to each other to cause them to aggregate. Once they aggregate, they stick to each other. And you see them flowing in and forming, and they form an aggregate, and that aggregate as a whole will then migrate. And they then differentiate the stalk and the fruiting body. And that entire process has been simulated by Nick Saville and Stan Murray, who were in the group of Pauline Hageveg at Utrecht University. And so there actually are simulations of the entire process of this. And then also Dr. Vasiev, who I believe is now at Edinburgh, has done simulations of that. So that's been done pretty extensively. I've always wanted to implement those simulations again in CompuCell. There are two issues. One is CompuCell is a bit slow for very large simulations in 3D. And the other one is that they have to implement rather fancy chemotaxis rules. And you'd have to write an extra extension to the diffusion solvers for that. If you go to a lower resolution image, let's see if I can point to this thing. That's fine. Where did my cursor go? There's my cursor. If you go to a lower resolution image, this is the same system, but looked at over a very large field of view. And you see the formation of these spiral wave patterns, oscillatory spiral wave patterns. Those are density fields of and orientation fields of the amoeba. So in here, where we saw the cells aggregating into one aggregate, at the center of each of these circles is one of the places where the cells are all flowing in to aggregate. So that's classic chemotaxis. And as I say, there are simulations of all of these processes, some of which maybe could be replicated in CompuCell. There are a couple of toy models in the demos that try to do some of that, but they're not very satisfactory. So what's the simplest possible assumption we could have for chemotaxis? The first the simplest possible assumption is, first of all, the chemical field is diffusing everywhere, and that the cells don't affect the field at all. But the cells can read the field at every point, and that the chemical field exerts a force on the membrane, on the boundary of the cell, that's proportional to chemical field gradient. So the force is minus lambda chemo times the gradient of the chemical concentration. And that would depend on probably on the density of the receptors. Now, in principle, the receptor density might not be uniform over the cell membrane, but that's something that we have to do extra work to simulate. So this seems very simple. This is actually exactly equivalent to chemical potential in chemistry. It's treating the concentration as chemical potential. But it has some perverse effects. If the gradients are very steep, the cells move infinitely faster, they break apart or disappear. The cell doesn't carry the chemical or push the chemical out of the way. That one is a hard one to fix. And the cells also don't remove chemical from the environment. So you're assuming that the chemical concentration is large. Well, the chemotaxis by itself doesn't take the chemical out of the environment.
It was like said the cells with up to
Right. So
smaller.
Let me be clear. So far I've been talking about biology. Now I'm talking about a mathematical model that's trying to simulate chemotaxis. And so this is the simplest possible thing you could do in which the cell moves in response to a chemical. So, and most simulations use something like this. I think Physicell uses this, and doesn't do anything more complicated than that. And for a lot of things, that works just fine. But I'm pointing out that there are some situations in which we know that this isn't going to work properly. And so we want to be aware that this very, very simple model of chemical cells responding to chemical gradients may not be sufficient. So just the way when we had the target volume too big compared to the target surface, the cell would get frozen. The target volume was too small compared to the target surface, the cells would break up or they'd freeze, these kinds of things. We have to be aware that when we use these very simple approximations to chemotaxis, we can get some artifacts, some incorrect results. Again, that's not to say you couldn't start with the simple one and see how well it works, but you have to be aware that it can fail. Okay, how does this work in CompuCell? Well, the simplest thing to do is you say that there's an energy associated with a chemical field that is lambda chemo times the concentration at the boundary of the cell. At the boundary. Now, the problem is there are a lot of different ways you can measure chemical concentration at the boundary. And it winds up that the way cells move are very different. So do you measure the concentration here and the concentration here? Do you measure the gradient of the concentration at the boundary, which winds up being different? When the cell is, in reality, the cells extend their boundaries with actin polymerization. But the retraction of the boundary of the cell is passive. It's not actively driven by the polymerization. And so typically we're going to wind up saying that we evaluate the chemical effect when the cell is extending, but not when it's retracting. And there's a switch that you can do in CompuCell and many other simulators that say, do you evaluate the chemical gradient only on extension or both on extension and retraction? biologically, the extension only seems to be correct. And Dagmar Eber at Zurich has done a lot of simulations to try to explore what the differences between all of these hypotheses about chemotaxis are.
So far, like the only extension and counting only extension and work better.
It usually, well, so they're perverse things. So suppose you have two cells
Mhm.
that are in contact with each other,
Mhm.
and there's medium on either end.
Mhm.
If I have the simple rule, then the boundary with the medium, if the cell moves forward, I change the energy. Because I go from the cell is here, there's cell here, and now it's here, so the concentration is different. But suppose I have the boundary between the two cells. I go from having cell here and cell here to having cell here and cell here. Because the boundary between the cells moves, but I still have cell at both locations. So if I'm just measuring whether there's cell or not and the concentration at that position, it hasn't changed. So if I evaluate the chemical energy, both on extension and retraction, then the boundary between two cells does not experience chemical gradient. It doesn't see it. If I do it on extension only, then every cell sees it. If I do it on extension and retraction, the gradient, the gain of the cell that's extending is balanced out by the loss of the cell that's retracting. And so there's no net force.
Oh,
So the result is that in both cases, the cells will move up the gradient. But in one case, as I add cells to the chain, the thing moves slower. And in the other case, the cells move at the same speed, independent of how many cells there are. So if you want to think about it, if you think about an old-fashioned train where you have a locomotive in the front and you're pulling cars, let's say, with coal.
mhm.
The more cars you add, the slower the train goes because the locomotive's still pulling the front. The classic rule like this, only the cells touching the medium pull. The things behind don't. On the other hand, a modern train like the high-speed train, some high-speed trains or a subway train, every car of the train has its own motor and behaves independently. And so in that case, the system doesn't slow down as you have more. So again, all of this is, I'm giving you maybe too much detail now, but I'm always torn a little bit about whether I should give you say, let's just do the simple thing and see what it does, or whether I want to let you know from the beginning that we always know we're making simplifications when we do modeling. And you're very sophisticated, and so you've done modeling. And so I want to call your attention to places where those simplifications may be an issue. Now, until you do it, it may not be so clear why it's important, but at least you'll know that you need to look out for problems. And then maybe you can come back to these slides. We really need a textbook, which has all of these slides as a textbook, so that we can organize these things. All right. So now let's actually look at the chemotaxis steppables and things. I said steppables, I should say plugin. As usual, we're going to have the trick of whether we specify things in XML or in Python. But there'll be a plugin called Chemotaxis. We have to say what the chemical field is that we're responding to. And then for each cell type, we say, what's the cell type? How strong is the response? And then here, it only chemotaxis at surfaces between the cell and the medium. And then there are a variety of other flags, which I don't remember all of because there are a lot of them, that say do chemotaxis only on extension, and there are a variety of other flags. But that's the basic one. So let's do a simple simulation where you could create a simulation which is, say, 200 by 100 lattice sites, and then I would say make it periodic in this says in the X and the Y direction. I don't think you want it to be periodic in the Y direction. Let's see.
On that direction, and
Well, okay, so sorry, I should, the cell lattice could be periodic in both directions. That's not a problem. You don't want the chemical field to be periodic because you want to create a gradient, and so you don't want the chemical field to be diffusing around the edge. So why don't you see about that? And then once you've got a chemical gradient and the cell, you can change the lambda chemo and see how it responds. Okay. Let me just, maybe better to, let me walk you through the steps here a little bit. So if you are going to do this, first you want to create the simulation wizard. You're going to need contact energy. You always need contact energy. You need volume, flex. You're not going to change those, center of mass. You're going to need a chemical field. And you need to turn on chemotaxis. You need to check this box here, chemotaxis. All right. And then you have to change the boundary conditions. And nowadays, the wizard should ask you about the boundary conditions for the chemical field, which it didn't used to do. And you should get something that looks more or less like that. And if you need help getting that, we can go through that. What do you do? Were you able to get that?
I didn't get that yet, because like here's where
Okay, what happened? Did it crash on you? Okay, sorry, I can't see can you just put the screen, can you put it up a little more? It's okay there. No, it's just a reflection I could. Okay, so, yeah, so.
Zero and the diffusion will be one.
Yeah, so you don't, well, so if you're gonna do a linear gradient, you don't want any decay. So you want to set the decay to 0. And you want the diffusion constant to be the same everywhere, and you want to make it, 1 is fine.
I changed it before,
And
but
you want the initial concentration to be okay, then you'd want to be, yeah, you can type in an expression. So you could say, how many voxels is it across?
200 by 200.
200? Well, yeah, you don't need 200 by 200 because I'll run slower. It doesn't do any harm. So you want to go from 0 to 10 in 200. So you want the concentration to be, let's see, 0 to 10 in 200. So you need 0 to 1 in 20. So you have 1 over 20 times x. So it's just x over 20. Instead of typing 0 for the initial concentration there, type x over 20.
Oh.
X over 20.0.
So here's
Oh, no.
This is like for specified the volume.
Huh. Oh, try, let's hit okay. This may be a bug because this is a new feature. Try hit okay. And now type, well, if you type X, it complains.
Yep.
Okay, Pedro, there's a bug in the new version of Wizard. In the chemical field specification, if you try to type an expression, it complains. Did you know that?
Can I see the expression?
Well, she's trying to type X over 20, and it says you can
Oh.
only have numerical characters.
Mm. What version is this? 4.8 or 4.7?
407.
407?
Hmm.
Well, the 8 was just released yesterday, so.
Yeah.
But it's a wizard problem. So just leave it at 0 and then we'll hand edit it to be whatever it needs to.
Okay, and the rest of is okay.
The rest of it is on the Y, we want constant, no, so we want constant value on the X, we want periodic on Y. On Y, we want periodic.
Oh, okay.
And Z, we don't have an option. Okay, that's fine. Okay, now for chemotaxis, we don't need, this is fine. We're just gonna leave it the defaults. That's fine. So, but we need to add entry because otherwise there's nothing.
Entry. Oh.
Yeah.
Oh, okay.
All right.
Um,
But that does seem to be a bug that it'll only allow you to enter a numerical value for initial concentration. I can check whether it does that on my
okay.
on my new version of Twitter. Which works because I've been running things, but I haven't tried actually creating a new simulation, so I don't know. I don't know about well, I'm not going to do that now, I don't think. What are you seeing on the screen share, Pedro?
That is still like the Aqua system.
I see the slides.
Okay, that's fine. Let's see. Okay. Yeah, no, it won't let you type. It won't let you type expressions. Okay. All right. So you have to hand edit the initial condition. So it's in the XML, you have to go to,
XML.
yeah. In the initial condition, yeah, you want that to be X over 20.0. Yeah, that should do it.
X over 20. Oh,
Okay. Okay, they're running that.
It's just the. So I was trying to do it in my belt.
So you wanna look at the chemical field?
Um,
Just look at the chemical field. Okay,
Yeah.
so it's fine, but you want to create only one cell, so you want to
Oh,
edit the.
okay.
We should also have a wizard that lets you edit the blob
Oh.
initializer settings. And you probably want to put the cell all the way near the near x equals 0.
Yeah,
Okay, at the left side of the,
the center, the center.
yeah.
Okay.
All right, so now let's run that and see what it does.
Because I.
What did you set for the volume constraint?
Okay, so maybe.
Well, you need to, where's the volume? Where's volume?
I choose that, but again, maybe I need to. Yeah.
So you can just add it. Where's your cursor? I'm sorry, it's next time, please run Zoom, because otherwise it's really, if I can't, it's much easier if we could screen share. So put your cursor, say line 46. Somewhere outside of the pixel. Okay, now let's go to plugins, volume. There you go. Oh, it says it's already defined. Huh. So set replace. Okay. You somehow pasted it in the middle of.
You just keep it right, so you don't define it in Python.
No, but it can't be inside of another plot. You've got it in the middle of another module, so you have to put it somewhere. There you go. That's fine. There's fine. Okay, that's okay. Make lambda volume a little bigger, like 5. Okay, now try running. All right.
What is just like
Okay, so
quality?
no, but what are the boundary conditions for the cell? It's stuck on the boundary, so you didn't have periodic boundary conditions for the cell lattice.
Yeah, I think I did something. For cell, I think it's something.
So you need periodic boundary conditions for the cell. I mean, you don't need it, but the cell is stuck to the edge, so it's not gonna do it well. That's at the beginning. It's in the POTS block, yeah, I mean, and yes, it's there, and I never remember it's periodic, and I just have to look that one up.
This is for the diffusion.
Yeah, no, you need it for the cell lattice. Look up the top.
But this is
Yeah, you don't have it. You don't have it there. Okay, so let me find it.
Because I just said it is periodic, so I have to like assign a periodic label for this.
Right, in the POTS specification, you have to say that it's periodic. And that's, let me get that for you. It's true here. Where is? Here, boundary underscore X periodic, boundary underscore Y period.
Just open my. Oh, great. I'll just restart it. So now, it was okay.
Yeah, there you go. Okay, good. So now you could try changing you can do this you could do this in the model editor because everything is in Python. I mean, sorry, in XML. In the model editor, in player,
Oh, okay.
open the Chemotaxis one,
Mhm.
and you should see lambda chemo.
Mhm. Chemotaxis.
Yes.
Okay.
Okay. So now what's the value that you have at the
Now
moment?
it's 500.
All right, so make it 1. And remember, if it was 500.0, you have to type 1.0. If it was 500, you have to type 1. Make it 1. And keep let the simulation keep running
Okay.
and see what happens.
So it's
Cell's not moving. Okay, now make it 10.
I still like didn't see it.
Okay, make it 100.
Now it's like
Now it's moving.
moving a little bit.
Okay, now make it 1,000.
It's definitely
Okay, now it's moving. Okay, now it's stuck at the far map. Now, so we'll have to start it again because it got stuck on the end. So now restart. And now let's make it, instead of 1,000, to make it 20,000. I mean, you can always edit the simulation code instead of the model editor, but it's a little faster to do this. To make it 20,000, now hit run. Well, that's actually working pretty well. So 20,000 still okay.
because now 20,000 is 2,000. We just added
Yeah,
one new.
okay.
Doing this stuff. Maybe restart it.
So it looks like you still don't have periodic boundary conditions. I don't know what happened. Why do you not have periodic boundary
Maybe
conditions?
I add periodic on X, not Y. No, but this is X.
Yeah, it's always a little confusing to remember which is which, but in this case you want them
Yeah,
both.
because you have like orientation would be.
But it'll also get stuck because there's this discontinuity in the chemical concentration between the left and the right boundary. So it's okay.
I think I initialized with the correct choice
Yeah.
because now we stuck at the beginning.
So
So I change back.
okay.
But it's still 500, right?
So hit pause and now make it, I don't know, 30,000, something very large.
Just restart it and then change the time.
Or just change it in the XML. That way you don't have to fill. I mean, I was trying to make it easier, but if it makes it harder to do it in the player, then just change the next.
I actually like to change parameters in XML. Still like
That's 30,000. Okay.
30,000.
Okay, so that's still all right. So I will just tell you, if you make it too big, the cell will disappear.
Oh, I think you could just
The
change
cell
all
will,
the
the cell will
functions.
break.
Okay.
Okay, so now the next thing you want to do in your code, save your code, is add a plot of the position of the cell versus time. Okay, just the x center of mass position of the cell versus time.
Um, Cell motion or cell position. Okay, please.
And again, you can always use the code snippets to do that.
Center of mass.
Sorry?
Center of mass. How do you like get the position center of mass?
Cell.xcom.
Oh,
It's on the screen. But
Oh,
it's also,
sorry.
if you look up cell attributes, it'll tell you to.
oh, it's called. Okay, center of mass. Yeah. Oh, oh, it's already there. Oh. Let's see if the
Where's the plot?
didn't show up yet. Because just the name is different. Try that. Oh, crossed.
Now you have a typo some.
It's not zero and position.
Did it leave an error message when it crashed?
No, I think
Let's see.
wrong.
Let's look at the
Let me just let me try. Oh no, not this one.
run it.
Okay. And then go back to check.
Um, okay, so that's definitely a typo in the plot definition. Let's look at your code. Self-dot plot window, add new plot window,
That
position
I-
versus
That,
time.
this type of, doesn't matter.
That doesn't matter, the title doesn't matter.
Yeah,
X position, hold on. Linear. Position. Style. Use dots rather than lines. That won't make any difference, but use dots in line 18. In line 18, use style equals dots.
oh,
But that's not where the problem is. The problem is in the plot where you're adding the data point. So let's look at this. Scroll down. So let's look in line 36. What is wrong in line 36? 36 mcsl.xcom. Plot line add data point. That looks okay. Let's see, why would that fail? Position exists, the name is position, position is okay.
yeah, but
Looks all right. What is wrong with that? Oh, no. Why are you crashing?
should I just, turn off this and try to relaunch?
No, something. So what I'm not sure of is whether it's. Is it in the plot win? Can you scroll to the right so we can see the end of the line? Okay, fine. Linear grid false.
These are all like,
The defaults.
yeah, like from this net, so.
Yeah, it should be.
English.
It looks
Oh,
okay.
I see, you put them in the start.
Oh, where's so?
I
Oh, you put it in
can-
the init? No, okay, so no. It's gotta be in the start. Nothing goes in the init except
Like this net.
tracking function. You know,
um,
it tells you where to put it, actually. It always tells you where to put it.
But it does.
Start.
Just put in.
It
Oh,
says
start.
start.
Okay. I'm confused on some of this. Okay, here it is.
Okay.
Oh, wait.
Okay, there you go.
No.
Good. And then it gets stuck. So now you could run it a couple of times with different values of lambda and see the velocity is constant, right?
You mean like for this?
For that situation.
Yeah.
Let's make lambda very small. Make lambda point. Let's make lambda. You started with what is the value of lambda now? Lambda chemo.
30,000.
30,000.
Yeah.
Make it 1,000. Because other thing you'll see is that if lambda is very big, there's a speed limit. The cell can't go faster than about half a pixel per Monte Carlo step. And so if for small values of lambda, the speed will be proportional to lambda. When lambda gets to be too big, the speed will be constant. So it's a little hard to tell because you maybe screenshot that image or screenshot that yeah, there you go.
And it's still
Okay, now run it with a different value of lambda.
1,000.
Okay, 1,000 is a good choice. You see, there's a lot more fluctuation. And it's still linear, but it's slower.
Yeah,
And it's
it's
stuck.
more than-
What time did it get stuck? To hit pause.
like around a little bit more than that, maybe like
About 1,000.
1100.
Okay, and what time did it get stuck with the bigger value?
This one here is less than 900.
Yeah, but it's still not 330 times faster. It's a little faster.
Yeah, it's a,
Okay,
it's a
but
little
not
bit.
that much. Okay, now let's make make it 100 instead of 1,000.
Mm,
Now what you'll see is as you turn down the lambda, it's slower and the fluctuations are bigger.
mhm. And I think maybe for this there was just there's so much more.
That's 100?
Yeah, I had to. It's stuck. It was stuck.
Oh, well, that's because, okay.
Why it's stuck?
Why is it stuck? It shouldn't be stuck. Well, start with it. Don't put the cell right on the edge. Move it in a little bit.
Okay. Oh.
You don't want it touching the bed. You don't want it touching the edge because of the discontinuity of the field. I mean,
Now
getting
it's-
stuck is interesting, but it's not what you want. So, okay, so now run it. Okay. So now it's moving, but pretty slowly, and you see there are a lot of fluctuations.
Mhm.
And that was for a value of what, 100?
Yeah, lambda is 100.
Yeah, so it's still chemotacting okay for 100, but it's slow. Now try 10. You could just, oh, okay, if you want to start over, it's okay too, that's fine.
Are you
Try
gonna,
10. You
here?
could, it's easier, it's faster just to edit the Python, the XML. Just make it 10. Or you can change it there too, it's fine, 10.
That's
And it really is 1/10 the speed. It's moving, but it's very slow. And you see the fluctuations are almost as big as the movement.
Yeah, like
So this tells you what's a reasonable range of lambda. 100 is okay. 10 is too small. 10,000 is okay. So for a range of lambda for these parameters, a range of lambda between 100 and 10,000 is reasonable. So you have a factor of 100 over which it works. And if it's too small or too big, it doesn't do what you want. And what you see here is a little bit, you see it gets stuck and then it moves and then it gets stuck and then it moves. That's typical, that's a typical lattice artifact for the simulation.
so it gets stuck as a lambda.
So here I've shown for some different values of lambda, you get different speeds and different slopes. So that's okay. So there's a really pretty simulation we could do, which is called the self-generating gradient, which happens in biology. And this simulates a situation in which the cells are following a chemical that's not freely diffusing, but it's bound to the extracellular matrix. And many growth factors, like vascular endothelial growth factor, actually behave this way. The cells secrete vascular endothelial growth factor, and it has a heparin binding domain. It immediately binds to the extracellular matrix. And in this case, the gradient is created because when the cell measures the chemical, it destroys it.
Oh, consuming.
Right. So it's sort of funny to think that digging a hole will cause you to move, but that's what happens. You'd think if you dug a hole, you'd get stuck.
Dig a hole like at the surface of someone.
Well, so what's going to happen is we're going to create a chemical field, and now we're going to turn the diffusion and decay constants to 0. And we're going to say that the cell has a diffusion constant inside of it of maybe 0.01 and a decay constant of 0.01. We're not going to do uptake because doing secretion and absorption by Python is a little tedious. So we're just going to say the cell takes up a small amount of chemical.
Mm.
And in this case, you really do want everything to be periodic, both for the cell movement and the chemical field. And see what happens. So what do you have to change? The only things you have to change are in the chemical field, set the global diffusion and decay constants to 0, and the cell diffusion and decay constants to 0.001 and 0.01. And make sure that the boundaries are periodic in both directions.
Mm.
And the initial concentration will make 1. We'll make a uniform concentration. Now, would you expect the cell to move in this case?
Mm.
The chemical field is constant everywhere.
Mhm.
Will the cell move due to chemotaxis?
No, there's no gradients.
So there's no gradient, but something interesting is going to happen. So try it. It's a physicist term, but have you ever heard the term spontaneous symmetry breaking? So suppose that I have something like a pencil
Mhm.
and it's balanced on its tip. It's going to fall over.
Mhm.
And when it falls over in some direction. But the direction is random.
Mm.
And some tiny initial variation in the position leads to a big variation once it's fallen over. So that's called a spontaneous symmetry break. Initially, the pencil's balanced, it's symmetrical. And then something small pushes it this way or this way or this way, and then it falls over in that direction. And so the error is amplified. The error is amplified. So let's see what happens in this case.
I was thinking because the cell is actually consuming, like, because
Yeah, it's consuming the chemical, but it's consuming it
it's
symmetrically.
yeah.
Right. But
So-
remember, the system is random, so it won't be quite symmetric.
Oh, okay.
And what's interesting is that that tiny random asymmetry leads to a macroscopic behavior. And this is an extremely important mechanism in developmental biology. Winds up, this is one of the main mechanisms in developmental biology for cell migration.
Oh, so for X, the diffusion feels periodic, so you just remove the boundary.
Now you need it to be periodic in both X and Y.
Okay. Um, and the initial expressions
Just 1 everywhere.
Um,
If you make it 0 everywhere, nothing will happen.
okay.
If there's no chemical, nothing happens.
Oh, okay.
You're not adding chemical to the system. The only thing you're doing is taking it away. Now, in later versions of the simulation, you could add a bias, an external bias. You could add medium as a source. There are a variety of things. Okay, so give it a try.
Diffusion reasons.
It doesn't matter, even if you set the diffusion rate to 0 everywhere. The only thing that matters is there has to be a decay coefficient inside the cell. All right.
Oh, this is my Gmail.
Is that the chemical field?
Yeah, one, cell one.
Okay, fine. Where's the cell?
Also like really close to stuff. Oh, I'm sorry, I'm gonna change it. I'm changing to 50. Why there's two cells?
Sorry?
Oh, like radius is 10. I see like there are two cells.
Okay, let's see. What's your initial condition? 550, 0, radius 10.
What is it?
Don't know why.
But that doesn't matter.
Make radius 5.
Okay.
10 is 2 cells. Oh, okay. Okay.
But like the radius is smaller than the wide, so it doesn't generate any.
It doesn't, should. Oh, well, I've changed it.
Yeah,
That's,
it's like, you can just run it. Just start with them cells.
all right, so you have to make it.
So, oh,
I would have used uniform initializer maybe instead of,
it's still like.
well, it's all right. 2 is all right. You
Okay.
can use it, it will still work.
Uh,
Okay, look at the chemical field.
mhm.
So hit pause.
Mhm.
Okay, now imagine there were only ones. Try making the radius 7 instead of 10. So it should draw just one. Again, I'm used to using uniform initializer rather than blob initializer.
Yeah, like still like use to.
The center position shouldn't matter. No, make the
No,
radius,
no.
okay, you got one, fine, right. Okay, good. Okay, hit pause.
Mm.
Now zoom in on where the cell is in the chemical field.
So
Tell me what direction does the cell move? What does the chemotaxis do? Does the cell move towards higher concentrations of chemical or lower concentrations of chemical?
how did also like moving to
Well, what did you tell it to do? What was the what was lambda chemo?
zero.
No, but are you telling it to move towards higher concentrations or lower concentrations? You did a simulation already, so does the cell move towards a higher concentration or a lower concentration?
So higher concentration.
Well, that's what you just did a whole series of simulations where you had a cell in a gradient. Did the cell move towards higher concentration or lower?
Higher.
Higher, right.
Yeah.
Okay, now look at the picture.
Mhm.
Okay, if I'm that cell at the bottom,
Mhm.
what direction is higher concentration?
So that direction has bigger chance.
Right,
Because the square little.
right.
doesn't
And
have-
behind it, it's blue, so that's lower. So the cell will continue to move forward because backward is lower concentration.
Mhm.
That's why it's called the self-generated gradient. The cell has destroyed the chemical behind it, so it has to move ahead.
Mhm.
Now, there's red over a whole range of directions, so it doesn't have to move exactly ahead. It could move to a slight angle. So,
Mhm.
but now, so keep running it for a bit. What happens? Can the cell cross its own trajectory?
I just like make a shift.
Zoom out
Okay.
so you can see what it's doing.
Oh, okay. For example, here,
Let it keep running for a bit. What happens when it tries to cross itself?
just turn.
It pushes itself away. Now what's going to happen when it tries to hit the existing trajectory?
Over here,
Yeah.
just power it into this direction.
Now, if it gets trapped, it'll randomly fluctuate until it gets out of the trap. But it basically, this is an algorithm. There actually is a volume, a space filling algorithm that works like this, where you're on a lattice and you say, look at all my neighbors and find one that has stuff in it and then consume it and then move to the next site. So this algorithm is used sometimes in image processing, for example.
But here, you see like it's stuck in here.
It got stuck.
So it's just like.
Now it'll go randomly until it finds red, and then it'll keep chewing on the red.
Oh,
So this is something bacteria really do. They'll explore the environment, use up all the nutrient in the environment. Where they can find the chemical, where they know where it is, they'll move in the direction of the higher chemical. If they don't know what direction to go, they move randomly until they find the chemical again.
okay. To see here, like, although like they're all being consumed, but here like the concentration is a little bit higher than here, so it just does.
Right. So then it'll do the best it can, but if it were really zero, it would just. And there's a persistence length. In other words, it's not moving in a completely straight line, but it's not moving in a completely random zigzag either. It's moving, this is what's called a self-avoiding, because it doesn't want to cross itself. It's not completely self-avoiding, but it's primarily self-avoiding, and it's what's called a persistent random walk. It's not a completely Brownian random walk, which has zero correlation length. And actually, there's a lot you can do with this particular simulation. This is typical run that you get, which looks like what you got. Now, in your case, we plotted the X center of mass versus time. What you really want to do is plot just the X and Y center of mass without not versus time. Just plot X versus X COM, Y COM.
Okay.
So you want to change just that one line where you plot the X COM versus MCS, just plot X COM comma Y COM.
The X-axis and Y-axis doesn't matter, right?
The name doesn't matter.
Okay.
I mean, you should really name it from MCS to X, but it doesn't. It's okay. It doesn't matter.
So the X-axis is actually the Y-COM.
Yeah, maybe it's better to read. Well, anyway, so do we better?
Okay.
But in any
So
case,
a pattern.
so you can see that's the position.
It's like moving.
Yeah.
Oh, okay.
Because it's rescaling. So right. So in this case, you can see in the blue exactly what you've seen here. Of course, it's rotated by,
Yeah.
but in a more complicated simulation, you might, for example, have multiple particles, or you might have the chemical diffuse, or you might have medium secrete more chemical. And so in that case, you might not be able to see the whole trajectory history. And so, for example, you could ask the question, what determines this? You notice that the lines don't cross, but they also have a distance separation between each other. What sets the separation distance between the lines?
It's the diameter of the cell.
Yeah, pretty much, but it also has to do with the fluctuation amplitude, sort of how much, because the cell diffuses around. So the actual size of the cell is, effective size of the cell is a little bit bigger than the actual size.
Yeah. Okay.
And you can see it's easier with the point cloud like that. When you see the cell try to cross itself, the lines cross itself, for example, it's a little easier to see. Now, as I mentioned, this is what's called a persistent random walk. And if I say this is a stretch exercise, or it's not something you want to do here. Although these days with vibe coding with ChatGPT, you could get it right away, which is, it's interesting to actually calculate the correlation length of the movement. In other words, if it were a pure random walk, the cell would be bouncing around in all directions equally at every time. In this case, it tends to move forward with some fluctuation. And so that defines a persistence time, which is how long does it take for the cell to lose a memory of what direction it was moving. And you could determine that by calculating the autocorrelation of the velocity. Now, to do that, you'd have to keep a list of all the positions of the cell, and then you'd have to run a correlation function to get the persistence length. And writing that code is a little bit of work. And that's something I wouldn't ask you to do that on the fly here. As I say, in the old days, it would be definitely a homework problem. These days, if you had ChatGPT or Claude running, you could say, give me Python code to calculate the persistence length if I have a list which has the X and the Y coordinates of the cell. And it'll give you the right code for that. But you still would have to run the simulation for quite a while because you have to have a pretty long time series to be able to get that estimated accurately. But so that's the basic simulation. Now, there are a lot of things, we're more or less out of time now for today, but I may assign some of these as homework. We could maybe try one of them now. If you add a small diffusion constant to the chemical field, then that pattern of high and low values will gradually smear out in time. And that means that it's easier for the cell to cross its own trajectory if there's diffusion in the chemical field. Also, if you make the diffusion constant very big, it's possible that you never get enough of a gradient for the cell to start moving at all. It smears out remember, this is fundamentally amplifying an initial random movement. And if you have the diffusion be too big, it destroys the initial randomness. And then if the medium secretes chemical, then over time, where the cell was goes back to being what it was before. And so then the memory of the trajectory is lost, and you lose the self-avoiding behavior. And so those are all, and again, all of these things actually do occur in real biological systems. So the classic example of this kind of directed migration is in development in the neural crest cells. So the neural crest cells start basically near the spine, well, near the brain, and then they migrate down along the spinal cord. And in fish, that they give rise to various, to give rise to the lateral line, for example. In mammals, they can give, they pattern the motor neuron trajectories. And so that neural crest cell migration, the cells have to migrate over a very long distance, and so diffusible gradients can't give you that patterning because the diffusion length for the growth factors is very short. And so you can't have the cells follow an external gradient of chemical because the signal doesn't get far enough. Whereas in this way, you can start the cells in a given direction with a little gradient to begin with. Once they start moving in that direction, they keep moving in that direction. And also then you can have other cells that actually follow the path that these cells laid down. You can't do that with you can't do that with the simple chemotaxis that we have here, but it's possible as well. So they can lay a track that the other cells follow. And so this is a pretty fundamental mechanism. Doesn't get modeled very often, somewhat to my surprise. Philip Maney has done with Paul Kulesa did models of this, some very nice models of it. So that's the self-directed gradient. A couple of things that I think we'll stop with. I know you said there were some other things you had to talk about tonight before we broke. Now, we've already gone for 3 hours. So, just when you're using the Chemotaxis plugin in Python, there's a self Chemotaxis plugin dot add chemotaxis data cell comma field name says this cell chemotaxis to this field. And then you can do things like set lambda chemo. And you can read the value and update it, for example. So it's possible to do that. And so one thing you could do with you're doing that, for example, would be change the value of lambda chemo every now and then with Python and see what the cell does. And there's a simulation here called chemotaxis dependence on parameters. So in your simulation, when the cell got to the end of the lattice, it got stuck. So what I did was write a little simulation where when the cell gets close to the end of the lattice, it flips the sign of the lambda chemo. So it crawls up the gradient, it gets close to the edge, it then crawls down the gradient, gets close to the edge, crawls back up, and so on. And so if you look at the student materials that's in lecture 9, chemotaxis dependence on parameters, I wrote a simulation that does that. And this is actually, remember we did by hand. I asked you the question, how does the speed of movement depend on lambda chemo? And we said if it was too small, the cell didn't move at all. I mentioned that if it's too big, the velocity saturates. And so what this does is it has the cell move forward and then flips the sign and also makes lambda chemo bigger, and then flips the sign and makes lambda chemo bigger, and it repeats that. Each time it does that, it puts on the plot lambda, the value of lambda, and the speed. And you'll see for low values of lambda, the cell doesn't move at all, or the dependence is very weak. And then between here and here, it's a linear dependence on lambda, which is what you'd like. And then if lambda is too big, there's a maximum speed of 0.24 lattice sites per Monte Carlo step. No matter how hard you push the cell, you can't go faster than that. And so if the force is too small, it gets stuck on the lattice. It doesn't move very much. If the force is too big, it runs into a speed limit, and then there's an intermediate region where it's linear. And so this is a useful plot because you want to say, what is a reasonable value of lambda chemo that I can use? so that the cell behaves properly. And this is telling you that that is between here and here. And so, and the code that I wrote, which is called chemotaxis dependence on parameters, it's easy to change that code so that instead of changing lambda chemo, it changed, say, the volume of the cell or the lambda volume or something else. So you can then map how the movement of the cell, if I make the cell bigger, does it move faster or slower? If I make the cell stiffer, does it move faster or slower? If I make the cell have more higher contact energy with the medium, does it move faster or slower? So this simple code that can be used to test the parameter dependence, the sensitivity analysis for all sorts of different parameters, not just for lambda chemo. And so the last thing, and I'm not going to do this tonight, but it's important, is suppose that we had an exponential gradient rather than a linear gradient. And that poses a problem for what we did, because where the chemical field is very small, the cell basically doesn't move at all. And where the chemical gradient is very steep, the cell will saturate like that. And so I'll skip down to it. There are a couple of there's something called logarithmic saturation, where you say that the chemical energy is actually lambda divided by 1 plus the concentration times the concentration. So this is now Michaelis function of the concentration. And you need the lambda chemo to be much bigger here than you do in the other one. So instead of 1,000, you're going to make it much bigger than that. And in this case, the linear chemotaxis, it doesn't move, and then it moves too fast. When you do this with logarithmic chemotaxis, in an exponential gradient, the movement is constant speed. And so this is adaptive, because before we had to say what lambda we have to use as a function of the chemical concentration. If we use logarithmic adaptation, the speed of the movement is basically independent of the concentration. It can follow a gradient almost at any concentration. If we change lambda, it still will move faster or slower, but it doesn't care about the absolute concentration anymore. And this is much more the way cells really behave. So that logarithmic chemotaxis is really the right way to do it for most simulations. All right. So I think for tonight, that's. I mean, I had more material, some of which we could do next week, but that was the main introduction to chemotaxis. Is there any questions about that or things you want to discuss this evening?
So for this scenario,
Yeah.
if the like for the right part, the gradient is very slow, and that means like the cells, like does the cell is the cell able to detect the gradient far, or actually just stuck there?
So you mean in reality, or do you mean in the simulation?
Both.
Okay. So what typically happens, there's a time element which is not involved in the simulation. Which is what typically happens with cells that are doing chemotaxis, is that when the concentration of the chemical is low, they produce more receptors for the chemical on their surface, so they're more sensitive. And then when the chemical concentration is high, they produce fewer receptors, so they become less sensitive. So they dynamically adapt their sensitivity. This assumes that the adaptation is instantaneous, that the cell changes its sensitivity immediately. In reality, there's a bit of a delay to that.
So, does that mean like more, because the physical property for the receptor to sense the signal is like, I think it should it be like decided by the number of the receptor, or because like I mean like the capability of sensing the signals could be added numerically. Because like more receptors, so you mean like more receptors mean more sensibility. But if like the signals are too far, I mean like if I have a lot of like too much signals, doesn't mean that I could sense the signals very far away. Right?
Well, so if the gradient is too weak,
Mm.
the cell won't sense it. I mean, there's some limit to how sensitive the cell can be. And so if there's really no gradient, the cell, no matter how many receptors it has, it won't find it.
Yeah.
If so you're right that if there's no signal, the cell can't sense it. On the other hand, I mean, at a macroscopic level, for example, insects sensing pheromones,
Mhm.
they can sense, moths can sense a few molecules, just a few molecules. Now, of course, if there are only two molecules, they don't know what the direction of the gradient is. And so they'll do something like bacterial chemokinesis, where they'll move in a random direction. And then they'll say, has the concentration increased or decreased? If the concentration is increased, you keep moving in the same direction. If the concentration is the same or decreased, you move in you pick another random direction and you try again. So what you're doing there is basically replacing a spatial measurement of gradient over a short time with a temporal measurement of gradient over a long time. So you're averaging over a long time because the signal is weak.
So is that kind of rule written in CompuCell, like the chemotaxis?
So if you want to do chemokinesis, real bacterial chemokinesis, we have to do that by hand. And that would be the next lecture, actually, which is, and that's how Physicell implements chemotaxis to begin with. Physicell can't do chemotaxis this way. What Physicell does is it measures the gradient that applies a force artificially to the cell. And it does it in a very strange way. I wouldn't have done it the way they do it. None of the other centered models do it that way, by the way. I mean, it seems to work okay, but it's not how the other people do it. But that's not a criticism of Physicell. It's because the interpretation of chemotaxis as a force on the cell is so complicated, because the reality is so complicated that different people make different assumptions about how to do it. But in CompuCell, you can apply an explicit force on a cell. You can apply a force in a given direction to the cell. And then you can measure the concentration at the first time and the second time, and say, if the concentration over time such and such has gone up, I keep moving in the same direction. If it's gone down, then I randomly pick a new direction and try again. And that will give you bacterial chemokinesis. So you have to do it by hand, because you have to measure, you have to decide when to change the direction. It's not built in, but it works fine. It does that. And that's more or less how Physicell does chemotaxis, if I understand properly. That it measures the gradient and then it applies an explicit force.
Thank you.
And And I'd have to look back at how Dirk does the same thing. He does it differently. I know that in his code. But I don't, it's been a long time since I've looked at the Physicel code and the other people's code. But it's different. I remember it's different. Again, because there are all these different options. Even within Potts model simulations, the way chemotaxis is done is different between different simulators. And so one of the things we've been doing in our open VT group has been looking at how chemotaxis is implemented in all the different simulators and trying to make sure that every simulator has all the same methods so that you can actually compare simulations.
Yeah.
Because otherwise it's really, you know, if one of them has chemotaxon extension only and the other one does it all the time, you can't get the same results. And so yeah, so next week we could do that the persistent random walk. You might want, maybe Pedro, that's something if you're there. We might actually do some ask ChatGPT to do if we give it a list which consists of the X and the Y center of mass positions, and ask ChatGPT to give us code to calculate the persistence length of that trajectory. That would be a useful module to have. And that's not it's a slight, doing that the base autocorrelation is not hard to write, but to actually extract the persistence length from it's a bit of a pain. And so it's not something I'd expect somebody just to pull out of the air to write. So that's one where I think having some coding assistance. In the old days, I would have said look in Stack Overflow for how to do it, because it's not code you want to write on your own. I mean, if you were doing a physics course where you were doing how do I calculate autocorrelations that we're doing the sort of the mathematics of persistence, that I'd say fine, write it on your own. But it's not. It's a bit complicated to do it. I mean, you did it with Rita, I think, for the persistent random walks for the cell, right?
Yeah, we have a bunch of code. I wrote some coding in Julia even to doing that.
That calculates the persistence length of the trajectory. But it's not trivial to come up with that on your own, I don't think.
It's annoying because you can first because you need a lot of data, and second because most of the usual methods don't use the entire trajectory, they skip points.
Yeah.
And then it can get messy.
Yeah.
But yeah, we do the persistence from fitting MSD and also from fitting the autocorrelation, the velocity of the autocorrelation. Both are valid.
Because if you do mean squared displacement, you're assuming that the movement is essentially Brownian, right? You're assuming it's diffusive plus drift. And if you use the autocorrelation, then that doesn't make that assumption, I think.
Both are valid. You can go back and forth between the autocorrelation and the mean squared displacement.
So then I'd have to think about that more. I would do it from the autocorrelation, I think, to get the persistence thing.
Yeah.
Anyway, I don't want to keep her here longer because she's already over time. But it does occur to me that it would be nice to have a demo that had that. Because I also wanted that just for the pure random walk case where you calculate what the diffusion constant of the cell is. And you've done that, I know. But here we're not trying to measure the diffusion constant. We're actually trying to measure the persistence. So the directed component. All right. Anything else you want to go over tonight?
No, I think for the microvolt, for that simulation, I modified the formula also. It doesn't show the scenario that I put in my homework. So probably I'll need to go back and
So, so also for that one, why don't you email Pedro
Yeah.
that text? Because Pedro, when I went over her homework for the bacterial cross feeding one,
Mhm.
and she did a nice job exploring a lot of different scenarios.
Nice.
But when I thought that was really pretty, but I didn't know exactly what you were expecting as answers.
Mhm.
And so I couldn't give a detailed critique of what she did. And so it might be, if you take a look at it, you might be able to give a little more detailed feedback than I did for that one problem.
Yeah, definitely. And since it's an exploratory exercise, we can
Right.
also meet and discuss it one-on-one if she's interested in developing something
Yeah.
more serious out of it.
Yeah, well, I think it would be nice, and if nothing else, we could rewrite the problem to be more, be clearer, and maybe do the analysis more. And again, that's the kind of thing where it would maybe get put into the CompuCell demo package. Would be nice.
Yeah. Yeah, it's a
Um,
beautiful simulation, I think.
yeah, yeah. So,
And
so
one quick thing before we break, James, on
yeah.
the rules thing, would you
Yes.
prefer having the hill functions min and max as fractions expressed as multipliers of the parameter, or would you prefer to have the minimum and the maximum having the units of the parameter?
No, I always scale everything out because otherwise, so I always prefer to have the velocity be multiplied by a number between 0 and 1. So the Hill
Right.
function is always a number between 0 and 1. Now it
Mhm.
may sometimes, for example, with Michaelis, sometimes it can go over. Well, it can't. The Hill function can't go over 1, but it never goes to 0.
In PhysicCell,
Exactly.
though, you can specify minimum and maximum. So you can have a hill function starting like from 10% of the value and go to like twice the value.
Okay. Well, I mean, I think we have to accept whatever PhysicCell did.
Mhm.
So I wouldn't change it. If he did it that way, I
All right.
wouldn't change it. Because you do
Okay,
you
so
do you do often wind up wanting to do an offset of the Hill function. So the Hill function intrinsically goes between 0 and 1, and then you
mhm.
scale it, you stretch it, and you may also slide it up and down. You might want it to be negative. For example, if the value is if the value of the parameter is small, you might actually want to be negative and then become positive as it gets nearer to the half max. Or it might even
Mhm.
want it to be negative both below the half max and positive above the half max, like a
Mhm.
tanh. Right. It
Mhm.
it
Yeah.
always depends on what you're doing with it. So I don't think there's anything wrong with being able to displace it vertically and to offset it and also to stretch it.
All right. Okay.
Um, I mean, I tend to start out with a Hill function that's between 0 and 1, and then put those things in myself, but building it in is fine. I don't have a problem with that. The one thing you do want to do, and again, if you're only doing single dependencies, it's not a problem, which is you often write concentration, variable to the n over k to the n plus variable to the n. And you really should divide through by the parameter. So it really should be variable over k to the n over 1 plus variable over k to the n. And the reason you want to scale out the K that way is because if you have multiple signals coming in that are not scaled the same, then K is inconsistent, right? There is no that you can't combine them if you have K plus X. Whereas if it's 1 plus x over k, then you can add y over k2 and it works. So you want to use the dimensionless form of the equation, okay? Now that, I mean, again, if Paul didn't do that, then you have to live with what he did. But it makes things more complicated. It makes it harder to do multiple signal integration if you don't do that. You could still do it, but you have to do everything by hand. Anyway, let's not worry about that one for the moment. Anything else, Pedro?
That's it.
Okay, anything for, great. Well, thank you always for being so patient. I mean, we sit